Welcome to my presentation, in which I hope to interest you in an alternative approach to design of arch structures, an approach based on analytical form finding. I'm Wanda Lewis, an emeritus professor at the University of Warwick, and the work I'll be presenting has been sponsored by the Leverhulme Trust. So what is form finding? Well, it is a process of shaping structures using or controlling forces developing in them. Many methods are possible, depending on the type of structure being modeled. For example, a soap film model as used in the design of Munich Olympic roofs, shown above, or a hanging fabric model which, when frozen and inverted, gives an optimal shape of a shell structure. And there are others. Apart from physical experiments, form finding employs computational and analytical form modeling. Why is form finding important? Because it can mimic natural objects which are known to be highly optimized in terms of their material efficiency, aesthetic quality, and durability. The main topic of my presentation is analytical form finding, with its focus on momentless arch forms. That is, arches developing pure, axial, compression, no bending moments when subjected to permanent load, that is, the arch and deck weight. The arches are pin-ended and they can be of constant cross-sectional area or constant axial stress, as discussed in my publications. Why permanent load? Because it is statistically prevalent, which means a structure shaped by this load will work in its optimum state most of the time. The analytical form finding model differs from a computational one in that it produces arch geometry as a function of the applied loads, axial stress, in the case of constant stress arches, and other input parameters such as the span and rise. I carried out several case studies, and one of them concerns the behavior of momentless arches of constant cross-section area relative to conventional forms, which are typically of parabolic and circular configurations. The results for a high-rise arch with a span to rise of 2 show that if we were to match the maximum stresses of the momentless form, the cross-section of the parabolic arch would need to be 2.5 times larger. It is surprising to see that, since the geometries of the two arches are very similar. Circular arch could not match the low stresses of the momentless form, so it is shown here as being 4.5 times deeper than the parabolic form. I have considered low-rise arches, and the momentless form still outperformed the conventional ones. Looking at the stresses, we can see that under permanent load on the left, the parabolic arch experiences high stress variation along its length compared to the momentless form. On the right, we see the results for the ultimate load comprising the deck and arch weight and a variable patch load of 50% of the deck weight acting on the left half span. In this case, we can see that the performance of the arches is similar. Overall, we can conclude that the momentless arch is optimal as it behaves better than the dictated form. This indicates that the currently adopted limit state design, which usually considers conventional arch forms in conjunction with the ultimate load only, produces non-optimal structures. In case study 2, I explored momentless arches of constant axial stress and compared their material efficiency with that of other arch forms, including momentless arches of constant cross-section. We can see that momentless forms outperform the conventional ones, with the constant stress arches requiring least material. However, as discussed in my latest paper, these arches can have a limited design space. In case study 3, I considered the iconic gateway arch in St. Louis and asked, is it a momentless form? Because of its varying cross-section, the architect called the shape of the arch a weighted catenary. He performed a series of experiments using a hanging rope with different weights attached to it to simulate the self-weight of the arch, but he was not happy with the resulting form and decided to alter it by eye. Surprisingly, this produced a mathematically defined shape that an American mathematician Osserman called a flattened catenary. We can see that the constant stress, momentless arch form, lies above the catenary and flattened catenary, so the architect's intuition that he may be producing an optimal arch has deceived him. In conclusion, it can be said that momentless arches are optimal because they have a low stress response to loading, a primary feature more important than the volume minimization criterion. Low stress response is found in highly optimized natural objects. Constant stress principle lies behind the growth of trees and tiger's claws, for example. Consequently, momentless arches have the potential to address durability and sustainability issues facing our future infrastructure. It can also be said that the current limit state design, relying on minimization of material within a dictated structural form and ultimate loads, does not produce optimal structures. Now I can see a number of challenges to the adoption of form finding design. First, using form finding at the conceptual design stage and linking it to the limit state design to ensure the structure is safe under ultimate load. Second, meeting very tight construction tolerances to ensure accuracy of shape and secure advantages momentless arches can offer. Third, reduction of short-term costs related to tight construction tolerances. Finally, I wish to acknowledge the Leverhulme Trust support in funding my work and thank you for your attention.